All right, so apparently there was a processing error with the video that I made for you guys last night. I apologize for that. That was completely unintentional, but I will go ahead and correct that mistake now. So we're wanting to graph the function secant of x. Okay, so what I'm going to do is I'm going to relate that to the cosine of x. All right. Now we know from the other day that I taught you guys that there are 5 important points when it comes to the cosine of x. All right, so this is what we talked about the other day, and I'll relate it to this unit circle chart over here to the left. We know that at 0, a radian degree of 0, the cosine value is 1. We know that at a radian value of pi over 2, that the cosine value is 0. So it's right here. Okay. Now I'm going to go ahead and graph one more point here, which is pi over 3 and 1/2. And you'll see why here in just a moment. Okay. Let's see here. Pi and -1. So that's here. So the graph would turn and go through here. And you guys know that I'm not perfect on my drawings. So just bear with me here. 3 pi over 2, 0 is here. And then pi over 2, 1 is here. So this is kind of the general form of a cosine graph. Okay. This is kind of what the base model looks like. Oh, there we go. Sweet, I didn't erase too much, which is what I wanted. Okay, so I put this point here, and there's a point which is 2 pi over 3. Where's my cursor at? There it is. 2 pi over 3, -1/2. So that's going to be about right there. There's another 1/2, -1/2 over here, and a +1/2 over here. Now, the reason why I am doing this is because I know that the secant of x is the reciprocal of the cosine of x. All right. So what we're wanting to do here is we are wanting to graph the same x values, but we're going to do the reciprocal of the y values. For instance, here, the x value is a 0, the y value is a 1. The reciprocal of 1 is 1. Here, the x value is a pi over 3, and the y value is a 1/2. So that's going to be up here at 2. Here, I have a y value of a 0. Now, when you have a y value of a 0, and you are going to take the reciprocal of it, whoops, oh, I messed up, I missed. Dang it, it was off. My eye moved just slightly. Let me start here. That means you're going to have a vertical asymptote. Oh, good night. That's not a vertical line at all. You get the point. I'm going to draw this on Desmos here in a second. So the first part of this graph looks like this. Then if I take the reciprocal of -1/2, that's going to be a -2, so that'll be down here. The reciprocal of -1 is a -1. The reciprocal of -1/2 is -2. And the reciprocal of 0 is going to get me this undefined area, which is going to be a vertical asymptote. So the graph is going to do something like this. Here, the reciprocal of 1/2 is 2, and the reciprocal of 1 is 1, and so the graph looks like this. So you can see how it kind of takes that pink cosine graph and it turns it kind of inside out, okay? Now, here's the real story here. These asymptotes, it's going to keep happening because you know that the cosine function is a periodic function, okay? Cosine just continues, whoops, let me change colors here to where I've color coded in the correct way. Cosine, it just continues to go like this, right? So every time it hits a 0, there's going to be a vertical asymptote, all right? So where is that going to be? Well, that is going to be every time we have n over pi over 2, where n is an odd number, okay? So let's go over to Desmos and let's look at this function. Okay, so we've got y equals the secant of x, and that's what it looks like. Now let's draw a few of these asymptotes. So there's pi over 2. Let me go ahead and move this over here. And then x equals 3 pi over 2. 2, there's another one. X equals 5 pi over 2. There's another one. X equals 7 pi over 2. And so that's why I said in my stipulation that that n in front of the pi needs to be a whole number. So we've got 1 half pi, 3 halves pi, 5 halves pi, 7 halves pi. The next one would be 9 halves. The next one would be 11 halves, so on and so forth. But you see that we have these vertical asymptotes as we go through our secant graph. And again, those are going to happen every time your cosine wave hits 0, right? Because the reciprocal of 0 is undefined. All right, so this is what the graph is going to look like. Now let me go ahead and take these out for a moment. And I am going to put in y equals the cosine of x, and you can see the way that the orange, boy, those are poor color choices. The orange secant graph is related to the red cosine graph. Okay. Now you guys know, because we talked the other day, that you can put a value in front here. And this value in front deals with the amplitude of the cosine function. Okay, so let's put this like this, and then let's play it. And here's what I want you to notice. You see these minimum values for the secant function, and they're also the maximum values of the cosine function, and likewise down here. Watch what happens. They're always connected. Okay. Now I know from our conversation the other day that your instructor allows you to use a graphing calculator. That's fine. But what if you don't? What if you don't get to? Okay. What I would suggest is to graph the cosine function and then to use those values to get the reciprocal. Let's go back here. Nope, here. So if the x value is a 0 and the y value is a 2, the reciprocal of 2, wait, yeah, no, we're not going to think about that way, because we already took the reciprocal here. The reciprocal of 1 is 1, and then we multiply it by 2. I'm thinking incorrectly here. Sorry, my morning coffee hasn't taken effect. Plus, I'm a little bit upset that my video didn't work yesterday. I apologize for that. So just again, notice that those peaks and the maximums of the cosine and the minimums of the secant, they are going to coincide. Okay. Now we also know that you can put a b value here that is going to either horizontally shrink or compress. Sorry, it's either going to go horizontally compress or stretch, thinking about the terminology that's used in your textbook, your function. Okay, so let's put this back to regular and let's play this. So notice as your cosine function either gets stretched vertically or gets compressed, I said the wrong word, either stretched horizontally or compressed horizontally, you can see that it has the exact same effect on the secant function. Okay, that's what I'm hoping that you see. All right. Okay, so now if we wanted to do the cosecant function, okay, it's going to be very much the same. It's not going to be exactly the same, but it's going to be really closely related. You're going to see what I'm talking about here. Oh, good night. I erased way too much here. Let's do the lasso. Lasso is going to make it easier. And then erase that and that and that and that. And let's go ahead and do that. Okay. So now we're going to do in purple y equals the cosecant of x, which we know that is related to the sine of x, because these two things are reciprocals of each other. All right. So I'm going to use a similar mentality here. All right. So for a radian value of 0, the sine is 0. That's here. For a radian value of pi over 2, the sine value is 1. That's here. A radian value of, whoops, I missed. A radian value of pi is going to be a -1. So that's here. A radian value of 3 pi over 2 is a 0, and that's here. And then for, where am I at? There it is. For 2 pi, it's back at 0. Okay, let me put my pi over 2 here and my 3 pi over 2 here. Let's see how well I can draw this. Wait, this is 0 here and -1 here. I misspoke. Okay, so here is our sine function that we talked about. Now, whenever we go to look at asymptotes, they're going to happen anytime that orange curve hits a 0. Okay? So those are my asymptotes. Now, if I want to go and graph this one, I'm going to have the peak point here, and it's going to rise up just like this. And here's the reason why. This value right here is a 1/2, which means that this one is going to be a 2. It's the same story as what I was doing with secant and cosecant. Sorry, secant and cosine. All right, so there's our graph. Now notice here that the asymptotes are different. Okay, the asymptotes are going to be n equals pi x, where n is an integer. So at 0 pi, 1 pi, 2 pi, back over here, -1 pi, okay, that's what it's going to look like. All right, so that's kind of why these graphs look the way that they do. And so let's go back over here and let's modify this to where we're looking at cosecant and sine. Okay, so you can see that they have that same relationship as secant and cosine. The minimum points here of the cosecant coincide with the maximum points of the sine, and vice versa down here. Okay, so if I go to stretching this or compressing it horizontally, it's going to do the exact same thing. Okay? If I vertically stretch or compress, the vertical stretch and compress of the cosine or of the sine function is the exact same as the cosecant function. Okay? So that's what I want you to see. Let's go ahead and put a plus a d out here, because this is going to slide our function up and down. Okay, where's that one at? Let's go a -4 to a +4. Let's step it at 1. And so you can see what's going to happen here. Okay, if you slide your sine function up or down, you will also slide your cosecant function up or down. All right, it's the same thing. All right, so again, if you're using your calculator to graph this, that's not necessarily a bad thing, but what if you don't? What I suggest is graph your sine function and then use your knowledge of how to graph the cosecant function as its reciprocal function. All right, so that's what I would suggest. Okay, now let's give an example of that. Okay, let's say that I am asked to graph y equals, let's go with 2 secant of 3x. Okay, so what I'm going to do is I'm going to relate this to 2 cosine of 3x. Now here, I know that my amplitude is a 2, and I know that my period is a 2 pi over this b value, which is a 3. Okay? So my 5 important points, they are now going to start at a 0, and they're going to end at a 2 pi over 3. Okay? Now let's get the x values first. Okay? Midway between 0 and 2 pi over 3 is pi over 3. Midway between 0 and pi over 3 is pi over 6. And midway between pi over 3 and 2 pi over 3, that's what, 1/2 pi? Okay. Then, normally cosine has a y value of 1, but I'm going to be multiplying it by this 2. So it'll be a 2. Then the next one is a 0, multiplied by 2 is a 0. The next one is a -1, multiplied by a 2 is a -2. The next one is a 0, multiplied by 2 is a 0. And the last one is a 1 multiplied by 2, and we get a 2. So let's see here. I'm going to pick, let's go with orange for my graph here. Now I need to put a line. All right, so let's see here. We'll call this 2 pi over 3. We'll call this pi over 3, pi over 2, pi over 6, 1, 2, and 1, 2. -1, -2. Just know that this isn't to scale, all right? Just bear with me here, okay? All right, so let's see here. Anytime I have a y value of a 0, I'm going to have an asymptote. Sorry, let me go ahead and graph this function just real quick. 0, 2, pi over 2, 0, pi over 3, -2, pi over 2, 0, and 2 pi over 3, 2. So it's going to look like this. So we are vertically stretched and horizontally compressed. All right. Now, anytime this graph hits 0, I'm going to have a vertical asymptote. Okay. Now if I want to graph this, I know that it's going to do this. It's going to do this. And it's going to do this. Using the knowledge that I created up here when I was doing the the secant and the cosine function. Okay, so my suggestion on graphing a secant function is to graph its related cosine function and then kind of do the reciprocal of it, which I call kind of flipping it inside out. Okay. All right. So that's how you would do those things. I would say also that you need to understand that the period here is the same thing as the period of your cosine function. All right. And these really don't have an amplitude because there's not a maximum value and a minimum value. So I don't really, yeah. Now, that doesn't mean that in a further example, you can't slide this function to the left or slide it down. But again, even if you're asked to do those things, I would graph your related cosine function first and then flip it inside out like I just showed you. Okay? All right, so now we're going to answer a question, which is, okay, here's this graph. Tell me what this looks like. Okay? So I'm going to go back here for a moment, and I am going to take away that, and that, and that, and that. I'm going to take away that, that, and that. Okay, so we've got the red function, which is cosecant. Notice that it starts off with an asymptote. Like if we're going from the y-axis to the right, it starts off with an asymptote and then gets another asymptote at pi. Okay, that's one thing I want you to key in on here real quick. And then we've got the secant of x, which is the black one here, and it starts off at 1 and then gets a asymptote at pi over 2 and then does all this stuff. So really, you know, the truth of the matter is these functions are quite related. Okay, if I added a pi over 2 to this, notice how those functions now coincide. They're on top of each other. Okay, but we're not going to do that. Okay, so it's just like sine and cosine, how they're the same shape. One of them is just moved to the left a little bit or to the right a little bit, whichever way you want to look at it. All right, whenever we're trying to determine which function to use, either secant or cosecant, I would say go back to your knowledge here to figure it out. Okay, now look at this graph. This graph, let me switch colors here. This graph starts off with a point of 1, and it has a asymptote. Now it's at pi over 4, so we've changed our period here. But notice that it starts off there. All right. So which one do you think it looks like, the red or the black one? Okay. So this looks like the black one. This looks like a secant function. Okay. So we're going to develop a secant function. Now, it doesn't look like it's shifted left or right at all, and it doesn't like it's shifted, whoops, I forgot the b value. It doesn't look like it is shifted left or right or up or down. So I'm not going to include a c or a d out here. All right. Now, if I were to graph its related cosine function, it would look like this, right? Okay. So what's this amplitude here? Well, this y value here is a 1. I don't know if you can see that. And that one's a -1, which means that this a value here is a 1. Okay. Now, if I want to determine how long it takes for this function to start repeating itself, well, it looks like it repeats itself if it starts at negative 2 pi and goes all the way to 2 pi. So if I look at this, that means that my period is a pi. Now remember, when we are determining period, it is 2 pi over the absolute value of a b. I would say in this case, we don't really need to worry about the absolute value. So what we're going to do is we're going to set 2 pi equal to 2 pi over b equal to pi. And I'm going to multiply both sides by the b, and that's going to give me 2 pi equals b pi. Well, the pi's can cancel out, and that tells you that b equals a 2. So my function here for this graph is y equals secant of 2x. You don't really need to write the 1. All right. Hopefully that is a fairly good explanation. Okay. All right. The next one here is a tangent function. Okay. This is from section 6, 4, I think. Okay. So this one is a tangent function, and they're giving us a few directions here. Let me choose a different color. We'll go with this one. We want to have a b value that's bigger than 0, and we're not going to have any phase shifts. What that means is we're not going to have a c value that moves this function left or right. Okay? So let's start by drawing just our regular tangent function. Okay? The regular tangent function looks like this. And it's going to have an asymptote here at negative pi over 2 and at positive pi over 2. And it's going to hit 1 and negative 1 at pi over 4 and negative pi over 4. All right. Notice that it also hits the origin. Okay. So what we're tasked to do is to figure this stuff out. Now notice I'm putting a d value here because it looks like it shifted down. We can actually figure out the d value really easily. If it's supposed to hit here at 0, but it really hits down here at negative 3, that means that that d value is a negative 3. Okay? Next, let's figure out the b value. Now, the period of a tangent function is pi over the absolute value of b. But again, we're not going to really worry about the absolute value part. We're just going to use a b. So what's the period of this function here? Well, it starts at negative 3 pi over 2, or at least what is pictured starts there. And it goes all the way to a positive 3 pi over 2. So when I add those two things together, I end up getting a 3 pi. So if pi over b equals 3 pi, and I multiply both sides by b, let's divide both sides by a 3, which is going to get me pi over 3 equals b pi. So if I cancel out the pi's, I'm left with a 1 here. And what that tells me is that my b value is a 1/3. Okay? So you just use this and relate it to what you find your period to be, and you can use that to figure out your b value, how it changes your what am I trying to say here? Your period. Okay? So far, here's what we know. We still need to put a number here. Okay? Now notice that my quarter point here goes from a 0 to a 1. Okay? That's because on a regular tangent function, we're not multiplying anything out here. Okay? And as it turns out, if I go from a value of negative 3 to my quarter point having a value of negative 1, I've also just moved up 1. So really, there's a 1 here for my a value, but generally you don't list that. Okay. All right. I know this video. Well, I would tell you this video is about 15 minutes shorter than the one that I did for you guys yesterday. But I have a class that I'm about to teach, and so I'm just going to have to cut this one off here. Your instructor will be in class on Monday. Okay. And I apologize for the mistake with that last video. It just processed incorrectly, and so it cut it up and only gave you 36 seconds. So once this one's done processing, I will send out another email that sends this to you. Hopefully, this gets you guys closer to being on track with your calendar, and your instructor will be able to guide you for the rest of the semester. All right. Thanks a lot for the opportunity to teach you guys.